Oh, thank you very much for inviting me here. Particularly, I thank Typhoon. I had not seen the Canadian Rockies before, and I was itching to see them. I was looking for an opportunity, and I did. They're truly magnificent. But even more magnificent was the Royal Tyrrell Museum of Paleontology. Now, Typhon kept kept talking about this museum in Drumheller. I said, what the hell is this? I thought it was a little, sort of local museum. They found a few dinosaurs. And finally, I realized he was talking about the Royal Tyrrell Museum. I said, why didn't you say so? He said, but it's in Drumheller. I said, yeah, man, who's ever had heard of Drumheller, for God's sake? It's lost in the Badlands. But the museum is important. It was truly a magnificent museum. I really enjoyed it yesterday. I mean, I told him it really made it worthwhile coming here, more than the Rockies. If you haven't seen it, I do recommend it. Typhon said, come and don't talk about geology, because there will be all sorts of people coming and listening to you. It was the same thing they told me in Chicago. They said, don't talk about geology, talk about something more interesting for the public. And I said, all right. I said, I'll talk about science, and I'll talk about how you make discoveries in science. The muse of discovery and the importance of the history of science within that process. Because, especially nowadays, in the latter half of the 20th century, science has become a vocation and a technical subject done by technicians sitting in their offices from 9 to 5. That's not how you do science. Science has a culture, and science is an obsession. If you don't have that obsession, never mind doing science. If you do science to publish papers, you're in the wrong place. I mean, you do science to make discoveries, and the papers are nothing but advertisement sheets for those discoveries, because then you want your colleagues to tell you you're full of shit, you haven't really made a discovery, you thought you did, but here are your mistakes, and you say, oh, thank you, you go on to the next discovery. That's science. Science is not citations, it's not publishing papers, it's not receiving grants, and it's not receiving promotions. Science is only and only making discoveries. But if you make the discoveries, all the rest come anyway. So, science is a way of acquiring knowledge about objects and processes, both external and internal to ourselves, okay, by reasoning beings. I don't want to say human beings, because soon computers are going to start practicing science, and we might even find some intelligence in the universe, okay? And the way science does that, I mean, the way reasoning beings do science, is that they generate testable hypotheses concerning the objects and processes they're interested in, and they test them by observation statements. This testing is what separates science from everything else. I mean, art is a way of seeing things. It's expression of hypotheses by the artist about what he or she thinks, feels, whatever, okay? But it's very subjective. I mean, religion is a hypothesis. It's commonly shared nonsense because it's not tested, okay? But science is not like that. Science is objective to the extent that it is shared by people who make observations and who can tell each other they got something wrong. If you get something wrong, that means you've come into contact with reality, because the reality showed you they're full of shit. Neither religion nor art can do that. Okay. This definition of science was first proposed by Sir Karl Popper. Okay. The fact that he's called Sir should not mislead you into thinking that he's an Englishman. He's an Austrian. He's a Viennese. But he ran away from the Nazis. He went to New Zealand during the war. And then Friedrich von Hayek, another Austrian who ran to London, hired him in the London School of Economics. And Celâl was such an important man. He was not only knighted, he was made a member of the Royal Society, at the same time a member of the British Academy, and then he became a Companion of Honor, which is an exceedingly rare thing even for an Englishman. I mean, Jesus, he was an Austrian. Popper published his idea, his definition of science, that is, it's a system of thought that functions by proposing hypotheses and then testing them mercilessly with observation statements, in this book. He had an earlier paper published only in 2 pages in Erkenntnis in 1933, but this book, although it says 1935, came out in in autumn 1934. Logik der Forschung means the logic of scientific discovery. It was first translated into English 1959, and many people agree that it's probably the most important philosophy of science book ever written. At least Einstein said that, Jacques Monod said that, Sir Peter Medawar said that, all the great scientists. They were all agreed that Popper finally got the correct definition of science. Einstein said the following. He published a popular collection of essays in 1931 called Mein Weltbild, means my view of the world, or my Weltanschauung. He said, in order to pursue science, you need 2 things. 1, you need to observe, know how to observe. You need to know how to test. You need to know how to make experiments. You need to know how to collect information, how to reach sources, how to use libraries, blah, blah. And he said, all of these things we can teach very well in schools and universities, no problem. But, he said, the more important second aspect of doing science is to make a discovery. Einstein said, there is no way to teach that. He said, somehow, you discover it. Every scientist discovers this for themselves, for herself, for himself, but it has to be a personal attempt. Okay, now, since there is no way to teach this, okay, so where do we get the muse of discovery? Where do we get the inspiration? I mean, since I'm a geologist, I emphasize you can get that in the field. Here's Albert sitting in the field. Actually, he's taken a bath, going swimming in Long Island in New York. Okay, but we geologists look like that sometimes when we're in the field, certainly not in Canada. And it's rather cold. I worked in Newfoundland many years ago, and my God, Newfoundland summer was Turkish winter. Okay. Or you can do science in solitary contemplation. You can find the muse of discovery there, or meeting with your peers. Well, these are the US Navy people talking to Einstein. Okay. You can do it in libraries. This is my preferred mode of operation. You can go on expeditions. This is the father's expedition Albert ever went. This is on the campus of Caltech in Pasadena, in California. He's riding a bike. Or you can even get inspired by being frivolous. That means all ways to discovery are permitted. You can come up with hypotheses using any excuse you like. To do science, to make it scientific, it has only one condition, that it should be testable by observation, and that it should be internally consistent. But it has to be testable by observation. That's extremely important. So, the question we're asking, when we ask about where we get our inspirations, what is the origin of hypotheses? Well, in 1896, the great American geologist Carl Gilbert gave an answer to that. He was a United States Geological Survey geologist. If you look at history of geology books nowadays, they'll tell you, James Dwight Dana was the greatest American geologist, which is rubbish. He was a Yale professor, and like most professors, he had a rather limited view of the world. Whereas Grove Carl Gilbert was a survey geologist. He worked with first with Wheeler Survey, then with Powell Survey, and he was the most versatile of American geologists ever. Up to this day, there is no American geologist to match this man's genius. He was incredible. He worked in every branch of geology with tremendous success. He created new branches of geology. And because in those days, the USGS was in Washington, D.C., and there was a Washington Geological Society. And in 1896, Gilbert was its president. So as president, he had to give a presidential talk. So he chose this topic, the origin of hypotheses. And he approached the question of, well, what is the initial spark? Where do we get our ideas? And his answer to this question was that it's analogies. That we see something and we say, this is similar to something else. Could it be not only analogous but also homologous? Could it have the same function? Could it have the same origin? Well, I mean, this may be complete nonsense, but it's the way to start. So you improve that by questioning your own hypotheses. That means you make deductions from that hypothesis. And every deduction you test. If your tests fail, then you say, all right, hypothesis was wrong. Let's go to the next one. Gilbert said, therefore, it was really analogy that helped us. Now, in my own experience, history of geology helped me find analogous cases to those under my consideration in any given time. So while studying solutions suggested to these old problems, I was led to new discoveries. And I will give you a few examples of those. You can say, well, I mean, can't you find your analogs in the current literature? No. Well, you can, but don't forget that the current literature is generated within the same boundary conditions in which you live. So, knowingly or unknowingly, you limit yourself. It is useful now and then to step outside those limits. Go to areas where many people think are unfruitful or have been unfruitful or were wrong, but try them again anyway. You may not necessarily find the answer there, but you might find an inspiration there. Alexander von Humboldt said that it was always a good idea to step back from the dogmatic stance of the present day and retreat to a time of mythology, even in science. He found it very useful. And as you recall, in the second volume of Cosmos, he actually dealt with the mythology as it illuminated science. Okay. The origin of rifts at high angles to mountain belts. Now, you know that in your petroleum engineering department, Professor Babadal, my host, works on fracture patterns. That fractures that originate at high angles to an orogenic front. And he very kindly gave me some papers showing the results of their research, and I said, have you cited Max Weber? He said, no. I said, why not? He said, well, we didn't know about him. I said, yeah, I know. Very few people do. But Max Weber was the first to realize that these extensional joints form 90 degrees to orogenic belts. And in 1976, I published a paper using the rift systems, 90 degrees to the Alps. And I will tell you where the inspiration came from. Here it is. Maximilian Weber, zum Problem der Grabenbildung, the problem of making grabens. Grabens are little depressions that are bounded by normal faults. Okay? He, already in 1921, realized that such structures, such extensional structures, form 90 degrees to maximum shortening. Okay? This was forgotten. And people like Hans Cloos, great geologist in the 30s and the 40s, he said, Max Weber is full of shit. These things do not form like that. And he thought they were forming by doming of the crust. Yet, when he drew a graben and a mountain belt in his textbook, very influential textbook, I mean, you realize this textbook that you're looking at now here got him the Penrose Medal in 1948, although he was German. Just 3 years after the war, Americans gave him their highest honor. He was a wonderful man. But look at him. Look, he was telling Maximilian Weber he was full of shit, but here is the mountain belt, goes in this direction, and here is the rift, 90 degrees to it. Well, if Maximilian Weber was wrong, why the devil do you draw it like that? Because observation demands it. That's how they form. This is when I was a second-year undergraduate student, the University of Houston. Not a very happy place, but I went to a meeting in Karlsruhe, in Germany, as an undergraduate. And I listened to the papers about the origin of the upper Rhine Graben. That's the upper Rhine Graben, right here. That's the upper Rhine Graben. That's the lower Rhine Graben. Right? And people showed that this thing formed exactly at the same time as this thing. This is a shortening area. That's an extension area, 90 degrees to one another. And yeah, they were still trying to justify this using Cloos's model. See, that's another thing you have to keep away from in science. What your teachers teach you is mostly wrong. Okay, so whereas here, they were still trying somehow to justify Hans Cloos, because Hans Cloos was such a great man. I mean, I see many Chinese faces here. In China, Li Shuguang was a great man. Li Shuguang was really a great man because he studied naval engineering in England. And he came up with some amazingly original ideas about the structure of Asia. But then Li Shuguang died, and everybody coming behind him, they didn't dare question him, with one exception, Huang Zhiqing. Huang Zhiqing he was a student of Émile Argan. Only Huang Zhiqing was able to question him, and as a result, he discovered the Daqing oil field. But the Communist Party didn't like that. So they said, well, it was really discovered by Li Shuguang, which is not true. Huang Zhiqing had discovered that. Okay. So you have to be ready to tell your teachers that they're full of shit. Really important. I mean, that's what I keep telling my students. I say, please, listen to me carefully and intently and with love. Don't believe a word of what I'm telling you. I say that we are like people lost in a forest. We all have torches in our hands. The only difference between me and the rest of you, I say, is that I have a bigger torch. I said, that doesn't guarantee that I find the way out. One of you may find the way out, and then we'll all have to follow you. Therefore, it was extremely important. When I wrote this paper, John Dewey and Kevin Burke, I mean, the geologists will know these names, two absolutely towering names in geology. They had used Hans Cloos's model to explain the Alpine foreland. And when I published this as a second-year undergraduate, I said, John Dewey and Kevin Burke are wrong. And everybody said, oh, you must be doing something terribly wrong. How dare you tell us that John and Kevin are wrong? And then when I met Kevin Burke, and I said, Kevin, this is what I think. Kevin looked at it. Yeah, you're right, he said. He said, we're wrong. And you may have seen that the second paper about this topic that deals with similar structures all over the world, not just in Europe, was authored by me as a third-year undergraduate, second author Kevin Burke, third author John Dewey. And then I realized that Kevin Burke and John Dewey were really great people. I mean, if an undergraduate comes up to them and say, look, you're full of shit, and if they look at the data and say, by God, you're right, let's move on. You know, that's the greatness of science. And that's why I immediately left Houston and joined them in Albany. I said, that's a much better department. Okay, the inspiration, as I told you, of that paper, you see, were these papers by Maximilian Weber. You see, I had the great advantage when I was a little undergraduate that I could read German in addition to English. And I had read these things that nobody had read. And I was able to say, how interesting, you know, let's apply this. And it worked. This is a much bigger discovery. This is what's called the Turkic type orogeny in the Altaids in Central Asia. And these are the three papers that we published. And the third one, as you can see, was published in Nature. It was the title story. It appeared on the cover of Nature. And there was a News and Views article by Bill Dickinson, one of the greatest American geologists. Bill died recently, unfortunately. But he wrote that. Now the question is, what was the inspiration behind this? This is the area. This is the Ural orogenic belt. The Caspian Sea is out here. That's Tibet. That's Japan. That's China. This is North China. And this is the Siberian Shield. And that's Lake Baikal is here. That's the Bryansk belt. Okay, the yellow area is the Altaids. Now, the Altaids are mountain belt, but it's not much of a belt, as you can see. It's more like a belly than a belt. Okay, so that's strange. And the next strange thing, that most mountain belts, you know, they're linear and long, etc., they have gneisses in them. These are hard rocks, hard, highly metamorphic rocks. Well, these mountains don't have those things. These mountains are full of schists and slates and mud rocks and deep sea rocks and basalts and serpentinites and lots of granites intruding. They don't have much else. And the poor Russians, after the communist revolution, they were cut off from the rest of the world. During the time of the Tsars, Russians had some fantastic geologists like Obruchev and Mushketov and Zaitsev and Inostrancev. These were truly towering geologists. And they did the geology of this area. Okay, and it is their reports that I read. Okay, and then came the communist wave. Now the poor communists had to become all originals because the capitalists would get it wrong anyway, so they have to get it right. But they got stuck with the models that had been developed in the 20s and the 30s by the French and the Germans. They didn't realize that people like Stille, Kober, Emil Ogg, they were retrogressive steps back into the middle of the 19th century. They didn't realize their own geologists and people like Edward Zeus had a much better idea of what was going on here. But in any case, I realized that in the current Russian literature, there was not much that could help me. They didn't understand it. The reason why I got interested in this is because, see, I was working in Tibet at the time. And when we looked at the Kwenlun, we realized that Kwenlun in northern Tibet is a very different mountain belt. It doesn't look anything like the Himalaya. It doesn't look like its continuation of the Qingling. It doesn't look much like the Pamir. It's a wide mountain belt with all the structures are steep. and it has very little gneiss in it. Okay, and the poor Chinese, they were doing exactly what the Russians were doing. They were trying to fit this mountain belt into the models that they had learned from the West. It didn't work. So, with a graduate student of mine in 1991, we realized that the Kwenlun looked more like Japan than anything else. We said it is a subduction accretion complex dominated mountain belt. It looks like where the one ocean plate goes under the other. And we said, oh, how interesting. Well, how far north does this style extend? And we noticed that this style extends from here. Ignore the Tarim Basin. It's a trapped little oceanic plateau. But it continues all the way into the Siberian Shield. And we said, how the hell do you make something like that? How do you make a mountain belt that looks more like a belly than a belt? How does that work? Alexander von Humboldt. Let's go back to 1843. Look what he says. Clay slates appear to be the dominant rock types of the Altai. He repeatedly emphasized the extreme paucity of gneisses and the dominance of not only slates but also various kinds of schists. He also emphasized the presence of granite in the interior of the schistose region. He was surprised there were not many gneisses. This is an observation in 1843. And nobody reads these things anymore. But I read this and I said, oh, how interesting. This is Humboldt's map, and Humboldt said, it's really interesting. The mountain belts become younger from the Altai from here. You can hardly recognize this map because this is supposedly the Ural Mountains. This is the Borortar that doesn't exist. This is supposedly the Pamir. That's the Kwenlun here. And this is the Altai, and that's the Tian Shan. Okay? And Humboldt said all these ranges become younger southwards. And when I looked at this, I said, oh, this interior region is just like the Kwenlun. And Edward Seuss, when he wrote Das Antlitz der Erde, this is the most important geology book ever published. 4 volumes, translated into French, translated into English, translated into Spanish, and the Italians started the translation. Typically Italians, they stopped after the first volume. They must have found it rather boring. You know, drinking your wine and listening to good opera probably were more fun than translating Seuss's German. Although Seuss's German is great fun. But anyway, look what he says. Now, you heard what Humboldt says. We may first observe that in these great mountains, as well as in the whole western part of the Altai, beyond the Irtish, not a single band of gneiss of any importance is known to exist. Indeed, this rock is seldom met with at all in these mountains, and never except a strictly local occurrence, a remarkable contrast to what is found in other lofty folded ranges. On the other hand, we meet with schistose rocks in surprising abundance, microschist, chlorite schist, and clay slate, the last named, with beds of limestone, and towards its summit Devonian or Lobocarboniferous fossils, which are found at many localities. These schists, like those in the Salair and Alatau, are pierced by granite, syenite, and porphyry, and diorite in dikes and bosses. In the contact zones lie many of the famous ore bodies of the Altai. Now, don't you think this sounds very much like Humboldt? And it was published here in the 3rd volume of Das Antlitz der Erde, which is 1901. And let's remember, Humboldt was 1843. This is Seuss's map. And in those days, of course, a lot more was known. This is Kwenlun. This is Chilianshan in China. This is Tian Shan here. And Altai is out there. And Seuss provided this cross-section across Asia. Ladies and gentlemen, the date of this cross-section is not known, but he died in 1914, so it's pre-1914. Okay? Please observe how the ocean is sinking onto the folded chains. This is the first suggestion of a subduction zone. And please notice here, a cross-section across Japan. Looks like that. This is the whole of Asia. This is only Japan. This is Thailand's cross-section. Okay. And when you compare these things, and then when you get even more recent cross-section, this is my good friend Maruyama sent me this cross-section across Japan. You realize, you say, Jesus, this is very much like Central Asia and the Kwenlun. And then you just go down the road from here towards the Olympic Peninsula to Vancouver. This is what you see on the ground. I mean, you don't see this. You need a seismic section line to do this. But this is a 40-kilometer thick subduction accretion complex. This is what it looks like internally after it's interpreted by some sensible geophysicists. And the rock types are just pillow lava, nanolimestone, bedded chert, red shale, varicolored shale, sandy fleece. This is Japan. But you say, my God, this is just like Central Asia. Okay. When I reread Zeus, I was struck by the fact that there was no regular variation of rock types across the strike in the Altaides. There is a monotony of this ubiquitous triplet, basalt, chert, turbidite, in vast areas invaded by tonalitic, granodioritic, and granitic plutons. And Zeus talked about the sea of more or less denuded folds. This man could not have seen a single satellite image. I mean, he died in 1914. But in his mind's eye, he could have seen that. He did see that. And here it is, today, with a satellite. And here is Zeus's map, taken from Hamlotzi. These are the maps. These are the folds of the Chilean Shan in Kwenlun. You see the same sort of thing. And when you come to Central Asia, in this mess, in this complete mess, you say many Japans are hidden here. How can we disentangle them? Okay? And you say, but Zeus gave us another indication. Look at Southeast Asia. These are the trend lines of the orogenic belt. Here, you can follow them by following structures, geological structures. But once the island disappears, what do? You're just left with the volcanoes. So, Zeus wrote the following. The islands and the reefs become less numerous as their distance from the peninsula increases, until at last it becomes impossible to discover the trend lines by which they are governed. But this does not always hold true for the volcanoes. Very often, we find that as a cordillera becomes concealed beneath the sea, the volcanoes increase in number. And it may happen that the cordillera completely disappears while curves of volcanoes remain visible and reveal the plan of the vanished structure. The farther out the trend lines advance into the ocean, the more distinctly they are indicated by volcanoes. Here it is, again. He's following the structure of the mountains using the volcanoes. And here we said, can we use here, remember we said there are many Japans hidden, but now they're dead. These are old things, 500 million years old, 300 million years old. But he said we can still identify the cores of these volcanoes in forms of intrusions. And he said, okay, let us follow them here. And this mess becomes simplified into this form. When you follow the magmatic front, as you do today in Indonesia, and then you do what you do, you take those units that you just saw apart, and by looking at the geology, looking at the continuity of these volcanic lines, you say, my God, there used to be a single arc. So that mess in Central Asia resolves itself into a single arc. And then you can interpret it. And then it makes sense. And then you can see how this whole thing was deformed, fragmented, and turned into the present-day Central Asia. I'm not going to bore you with the details of that. But you can see how, Just a few tips from Humboldt and Zeus by reading the history. You see, both Humboldt and Zeus had no idea of plate tectonics. They could not have known it. But they knew the geology. And they were able to give you a few hints. The trick is to catch those hints and use them as your inspiration. Welcome to paleontology. In 1927, there was an extremely unhappy German vertebrate paleontologist living in Denmark. His extreme unhappiness had two sources. One, Denmark has no rocks that has these old fossils, so the poor man had to go elsewhere. And because Denmark has no such rocks, it had no vertebrate paleontologists. And in the introduction to his book, Heilmann says, imagine the unfortunate lot of the vertebrate paleontologists sitting in Denmark with no colleagues to talk to. But he still wrote a book about the origin of birds. Okay, here it is. And in those days, Archaeopteryx had become very famous, and Darwin was vindicated. People said, my God, here is a bird that has little clutches, it has a tail, and it has teeth. It's a transitional form from reptiles to birds. And by God, Darwin must be right. And Darwin lived to see this great triumph. But Heilmann was not satisfied. He said, Archaeopteryx looks far too evolved. There's got to be another animal between Archaeopteryx and the reptiles. And he imagined that that animal would be a tetrapteryx. That means it would have 4 wings and a long tail. He, using Darwin's basic idea of natural selection and survival of the fittest, fitting of the NMR, he drew this in 1927. Ladies and gentlemen, 2009. Anchiornis huxleyi was founded by our Chinese colleagues. And my God, it is Heilmann's animal. Extraordinary. You can see the predictive power of the theory of biological evolution. Heilmann just used that to predict an animal. And that animal was found later. Going back into paleontology, reading Cuvier, his famous Recherches sur les ossements fossiles, 1912, ladies and gentlemen, please do read it. You will find incredible little tips to our present-day paleontology, to our present-day world, to our present-day events, when the Chicxulub crater was found, and the idea that the dinosaurs got wiped out with many other kinds of animals at the end of the Cretaceous, and a catastrophe. My good friend Ken Shu, I remember we were sitting in the ETH, and Ken was involved, and he thought it was a comet, and he published a very interesting paper in Nature about a strange love ocean. And Ken said, Celâl, he said, look, Cuvier was right. And I said, yeah. But I said, the strange thing is both he was right and Lyell was right. You can't say Cuvier was right and Lyell was wrong. They apply to different parts, to different times, to different scales. You have to be aware of that in order not to sink into the present-day dogmatism. You have to know the culture of your science. Goethe once said, the history of science is science itself. Science cannot be done without also doing its history, and history of science cannot be done without also doing science, for the simple reason that both go after the problems that interest science. Without the problems of science, there can be neither science nor its history. Science is not an accumulation of facts. History of science is not an accumulation of facts about scientists, or about facts of science, or about social circumstances that may connect the two. They're both about problems that science goes after in historical continuity. We scientists are the only people who try to create images of something that already exists and is therefore by definition perfect. I mean, if I'm trying to describe this, right, this already exists. I may not see the whole of it, but with my hypotheses, I will try to go after it until I satisfy myself that I found a perfect match. That never happens, but we come pretty close. But the ideal is perfect. It's there. Okay? Artists, businessmen, farmers, soldiers, clerks, clergy, they have to find out about the quality of their creations by doing all sorts of funny things, but they can never do it, even if they think they've achieved everything, because they're so subjective. Okay? They lack an external standard. Pursuit of sciences, therefore, is the most sublime and satisfying of all human endeavors. And ultimately, that's the only one that counts. All the rest are rubbish. I mean, art is extremely useful because it fosters creativity. That I like. I mean, that has to be there. But things like, religions, this is, I mean, we know that they're harmful. Not only that, but they're total nonsense. Utter nonsense. And when you look at these things from a perspective of science, this is, the social scientists call this sort of an attitude scientism with an element of belittlement in it. They're being silly. Because Bertrand Russell once said, there is nothing human beings know that had not been invented or discovered by science. The rest is rubbish. And in order to do science, you have to have the culture of science. You have to know its past. You have to know its not only successes, but also failures. But sometimes you learn from those failures. Therefore, you have to have a complete culture of science. Otherwise, you become just technicians and servants of the real scientists. Thank you.